Hello friends, I hope it is a good morning wherever you are, and IBM is here to welcome you to the last episode of medical physics, that is physics 9702, and this is solve the past paper questions where we are trying to understand and trying to get a glimpse into how these questions of medical physics are actually set. So do not forget to subscribe, share the video, download the document, print it, and practice on the hard copy document. That's how you're going to be able to pass easily. So in this episode of solved past paper questions, remember there are overlapping questions about ultrasound, X-rays, the CT scan, and in this episode we shall also see some questions about the PET scan. The PET scan questions are still new and they are still very few, but we shall at least have something to refer to. And they will not change much. They will not change much. So we should use this video to get a glimpse into solving questions in past papers in medical physics. So let's straight away move to our document. And I think we stopped on page 547. So let's move to 548 straight away. State what is meant by specific acoustic impedance. I think at this point, specific acoustic impedance is part of us. It must be part of us by now. So this is the product. The product of the density of a medium and the speed of ultrasound wave in the medium. So that's what we are calling a specific acoustic impedance. The product of the density of the medium and the speed of ultrasound wave in the medium. So that is Z is equal to density times C, where C is the speed of ultrasound in that medium. The density of a sample of bone is given as 1.8 times 1.8 grams per centimeters cubed, and the speed of ultrasound in the bone is given as 4.1 times 10 power 3. Calculate the specific acoustic impedance ZB of the sample of bone. So ZB for the sample of bone is going to be the density of the bone times the speed in the bone, which is going to be 1.8. Of course, we can remove the grams per centimeters cubed. We change it to kilograms per meters cubed. That is times 10 power 3 in kilograms per meters cubed. Then times the speed, which is 4.1 times 10 power 3. 4.1 times 10 power 3. So we press our calculator. So from my calculator, this is 7.4 times 10 power 6 kilogram meters per second, kilogram per meter squared per second. A parallel beam of ultrasound passes normally through a layer of fat and of muscle as illustrated here. So let us say the intensity just entering the layer of fat, I will call this one I naught. The intensity arriving at the boundary between fat and muscle, I will call it I1. The intensity just leaving the fat, the boundary, I will call it I2 because some has to be transmitted through the boundary. And the intensity which arrives at the other end of the muscle, I may call it I3. Okay. So the fat has thickness 0.45 and the muscle has thickness 2.1. Then they have given us data for Z values for fat and muscle. And they have given us the attenuation coefficients. They've given us attenuation coefficients. You also see that they are also close to each other. The intensity reflection coefficient at the boundary between the two media of specific acoustic impedances Z1 and Z2 is given by that. Calculate the fraction of the intensity of the ultrasound that is transmitted. You know, Cambridge bolds makes the what is very important or what would be confusing to a student bold, so that when you fail the question, it's not their business. Note that this is the fraction which has been reflected. So what is transmitted must be 1 minus alpha. If this is what is reflected, then what is transmitted should be 1 minus alpha. So therefore, the fraction transmitted will be equal to 1 minus the fraction which is reflected, which is going to be 1 minus. So Z for muscle was 1.7, Z for fat was 1.3 over 1.7 plus 1.3 squared. Remember it is times 10 power 6, but the power of 10 is the same, so we just ignore it. So this is 1 minus, I press my calculator. So from my calculator, this is 0.018, which when I subtract 1 minus that, when I subtract, this is 0.982 to 3 significant figures. Okay. State what is meant by attenuation. State what is meant by attenuation of an ultrasound wave. So we now know what attenuation is. Attenuation is the reduction or the loss in signal strength, loss in intensity, loss in power of the wave as it passes through a given medium. So the reduction in intensity or reduction in power of the wave, the reduction in the intensity or the power of the wave as it passes through a medium. So that is attenuation, reduction in the power or reduction in intensity of the wave as it passes through a medium. Determine for the data for linear attenuation coefficients are given in the table 5.2. We have seen that the values of mu are given. Determine the ratio intensity of ultrasound transmitted through the medium over intensity of ultrasound entering the medium for the layer of fat of this thickness. Intensity transmitted. Remember, intensity transmitted is equal to the incident intensity in that medium, e power negative mu times x. So for fat, we shall say the fraction which is intensity transmitted through fat over the intensity incident in fat is going to be e power negative. Mu for fat was given as 0.24 per centimeter. And since the thickness is also in centimeters, I will not convert the units. So it is 0.24 per centimeter times 0.45 centimeters. So I just press my calculator here. So this is giving me 0.898 to 3 significant figures. Then for the layer of muscle of thickness 2.1 centimeters. So again here, the intensity transmitted through that layer over the intensity incident on that layer will still be e power negative, the attenuation coefficient, which is 0.23, times the thickness, which is 2.1. The units are the same, so I will not convert. They will cancel out. One is per centimeter, the other one is in centimeters. Then I press my calculator. So this gives me 0.617 to three significant figures. Use your answers in B and C to determine the fraction of the intensity entering the layer of the fat that is transmitted through the layer of muscle. So in other words, we want I3 divided by I naught. That's what we want to find. Note, from the diagram we saw that the intensity transmitted through the fat, we called it I1. And we have already seen that I1 is equal to I1 was equal to I1 is actually, this is I1 because intensity transmitted through fat is I1 as compared to I naught. So I1 was 0.898 times I naught. This one here is I3 over, this is not, actually this is going to be I1 over I naught to be specific so that we don't move. Let that be I1. And this one is intensity transmitted through. So this is going to be I3 over I2 because I3 is what goes through muscle and I2 is what is incident in muscle. So to be specific, let's do it like that. Then I3, we have that I3 is the same as 0.617 times I2. Now remember, I want I3 over I naught. So I'm going to move backwards. But also remember at the boundary, we had that I2 over I1, that is at the boundary, intensity at the boundary. We have I2 over I1 there. I2 over I1 is this one here. This is I2 over I1. Intensity transmitted at the boundary, that was I2 divided by I1, if I1 is what is incident on the boundary. So we can now also add it here as our third equation, that I2 over I1 or I2 is equal to 0.982 times I1. Now we just do back substitution. I put I2 into the I3. So I3 is going to be equal to 0.617. Where there is I2, I'll put 0.982 times I1. And where there is I1, I will put I1 as that. So I3 is going to be 0.617 times 0.982 times. Where there is I1, I'm putting 0.898 times I naught. So the fraction I naught, I3 over I naught, which we want to find here, is going to be the product of these three. I'll just press my calculator. So from my calculator, this is giving me 0.54. So this is approximately 0.54. Okay. Alternatively, a mathematician would not waste time. A mathematician, this is just for mathematicians. If I3 over I naught is what we want, this can be I3 over I2 I have to remove I2, so this will be times I2 over I1. I have to remove I1, so this will be times I1 over I0. So just multiply, we have I3 over I2, you have I2 over I1, you have I1 over I0. So you multiply by all those three and you get the answer. Okay. State what is meant by specific acoustic impedance. This is the product of the speed of ultrasound, product of the speed of ultrasound wave in a medium and the density of the medium. The product of the speed of ultrasound wave in the medium and the density of the medium. A parallel beam of ultrasound of intensity I naught is incident on the boundary between two media, A and B. The two media A and B have specific acoustic impedances ZA and ZB respectively. The intensity of the beam transmitted through the boundary is IT. Show that IT over I naught, state how the ratio IT over I naught depends on the relative magnitudes of ZA and ZB. Of course, we know that ratio IT over, so the ratio alpha is the ratio of intensity reflected at the boundary over what is incident at the boundary, and this would be Z born minus ZB minus ZA over ZB plus ZA, and this would be squared. That is reflected. So it means I transmitted over I incident is going to be 1 minus ZB minus ZA divided by ZB plus ZA, and this is squared. That is IT over I naught. So let's now discuss the impact of the magnitudes. Let's think of ZB being many times bigger than ZA. If ZB is much greater than ZA, it means when I subtract, I get ZB. When I add, I get almost ZB. So this gives us a ZB over ZB, which is 1 squared. Then 1 minus 1, which is B, is going to be 0. So that means the ratio is approximately 0. So here, then the ratio is approximately 0 if ZB is much bigger than ZA. And then if ZB is almost, that is approximately equal to ZA, then if ZB is approximately the same as ZA, that means when you subtract ZB minus ZA, you get almost 0. When you divide 0 by ZB plus ZA, it is 0. So 1 minus 0 is approximately 1. So it means then the ratio is approximately 1. So that is how the intensity IT over I naught depends on the relative magnitudes of the Z values. The linear attenuation coefficient mu of B is 23 per meter. Calculate the thickness of the medium B required to reduce the intensity of the ultrasound beam to 34%. So we want the transmitted intensity to be 34% of its initial. That means intensity transmitted is 34% is 0.34 of the incident intensity. Calculate the thickness of the medium B required to reduce the intensity of the ultrasound to 34% of its initial intensity in medium B. So we want medium B to reduce the intensity to 0.34. So that means 0.34%, 0.34 I naught is what to go through medium B. We know that intensity transmitted through a medium is equal to I naught e power negative mu x. So 0.34 I naught is equal to I naught e power negative mu, which is 23, times the thickness x, which we want. I naught has cancelled, we introduce natural logarithm, so ln of 0.34 should be equal to negative 23 times x. So it means x is going to be ln of 0.34 divided by negative 23. My calculator. So this is giving me 0.047 meters to two significant figures. Okay, next. A parallel beam of X-rays of intensity I naught is incident normally on some soft tissue and bone as illustrated here. So you can look at the figure. We have intensity incident on the soft tissue. It goes through soft tissue, passes through bone, and it is transmitted. The transmitted intensity through soft tissue, the other side is I. So note that let's find the thickness. This is 1.8, bone is 0.4. So I think this is 0.7. This one is also 0.7, assuming the bone is at the center. The bone is of thickness of 0.4 centimeters thick, and the total thickness of the bone and the soft tissue is 1.8 centimeters. The intensity of the transmitted beam is I. They have given us linear attenuation coefficients for bone and soft tissue. They want us to calculate the in decibels, the ratio. Transmitted intensity I over incident intensity I naught. So I want us to look at this very easily, that when it is just entering here is I naught. Let us assume what arrives at the bone is I1, and let's say I1 also leaves the bone. And let us assume what is transmitted through the bone is I2, so I2 leaves the bone, and what is arriving the other side is I. So we're just going to use simple relations of transmission. Intensity transmitted here, it will be I1 equals to I naught e power negative mu x, I2 equals to I1 e power negative mu x, and I equals to I2 e power negative mu x. So we have done similar questions before, so this should be very easy. So we are saying I1, intensity I1, which is transmitted through the first part of soft tissue, is equal to I naught e power negative. Of course, we are going to be using negative mu x. So I1 is going to be I naught e power negative mu for soft tissue, which is 0.992 times the thickness, which is 0.7 centimeters. That is mu for soft tissue. Then I2, which is transmitted through the bone, is equal to I1 e power negative. Bone is 2.9. The thickness is 0.4. Then I, which is the final transmitted intensity, is equal to I2 e power. It is now again through soft tissue, so that would be negative 0.92 times again 0.7. So we want I over I naught. We want I over I naught, so we are going to do back substitution until we reach I naught. So I is going to be, where there is I2, I'll put I1, e power negative 2.9 times 0.4. So this is times e power negative 0.92 times 0.7. I've just substituted for I2. Then I remove I1 again. I1 is given as again, I1 is here, I naught e power that, so we shall just replace I1 again. So we shall have I naught e power negative 0.92 times 0.7, then times e power negative 2.9 times 0.4, then we have times e power negative 0.92 times 0.7. So press the calculator once. Pressing the calculator, I am getting I divided by I naught as being equal to 0.0865. Now we need the ratio in decibels. So the ratio in decibels, remember I said decibels is 10 log of that value. So this would be 10 log of 0.0865. So press our calculator again. So this is negative 11 to two significant figures. In decibels, it is negative 11. Okay. Outline briefly the principles of computed tomography. Outline briefly the principles of a CT scan or CT scanning. Okay, this is an easy scan. Remember, a series of X-ray images are taken for one slice in different angles. These images are in the same plane. The images are in the same plane, and complete two-dimensional image is formed for that particular slice. The process is repeated for different slices, and their two-dimensional images are also found. Then at the end of the scan, the computer enables the combination of all these two-dimensional images to produce a complete three-dimensional image, which can be viewed and rotated from different angles. That is a CT scan. That is a CT scan. Okay. So a series of X-ray images taken from different angles are obtained for one slice. For one slice of the organ being investigated. A series of X-ray images taken from different angles are obtained for one slice of the organ being investigated. Note that all these images are in the same plane. All these images So all the images of one slice are going to be in the same plane. So the images are combined. The images are combined to give. Images are combined by a high power computer to give a two-dimensional image, a complete two-dimensional image of that particular slice. The images are combined to give a complete two-dimensional image of that slice. The images are combined to give a complete two-dimensional image of that slice. So remember there are many slices to be investigated, so most slices are imaged similarly or in the similar way. Most slices are imaged most slices are imaged similarly. The images of successive slices are then combined images the images of successive slices are then combined using a high power computer. Using a high power computer to build up a three-dimensional image, a 3D image of the entire structure. A three-dimensional image of the entire structure or entire organ, which can be rotated and viewed from different angles or from various angles. Okay, so that is the CT scan, and it is the easiest scan, I guess, because it has very few simple steps. A series of X-ray images are taken from different angles just for one slice. The images are combined to give a complete two-dimensional image of that slice. Then most slices are also imaged in the same way. The images of the successive slices are then combined using a high power computer to form a three-dimensional image which can be rotated and viewed from any angle as desired. One section of a model designed to illustrate CT scanning is divided into 4 voxels. The pixel numbers K, L, M, and N of the voxels are shown here. You can see the directions of view. The section is viewed in turn from 4 different directions, D1, D2, D3, and D4 as shown there. The detector readings for each direction are noted, and these are summed to give the values 42, 45, 51, 30. So these are the final value of the sum of the final values. So I'll draw another table here in case we are asked to find the original pixels for K, L, and M. So the background reading is 24. So remember, we subtract the background reading. Determine the pixel numbers K, L, M, and N. So we first subtract the background reading and then we divide by 3 because we are taking allowance that more than one view or 3 more views were taken. So we shall have 42 minus the background, which is 24. The background is 24. The background is 24. So we have 42 minus 24 divided by 3. Here we shall have 45 minus 24 divided by 3. 51 minus 24 divided by 3. 30 minus 24 divided by 3. So for K, I think for K is 42 minus 24 divided by 3, that is 6. Then L is 45 minus 24 divided by 3, which is 7. M is 30 minus 24 divided by 3, which is that is 2. And N is 51 minus 24 divided by 3, which I think is 9. So you can press and check. So K is 6, L is 7, M is 2, and N is 9. So those are the pixels. Electrons in a beam electrons in a beam are traveling at high speed in a vacuum. The electrons are incident on a metal target, causing X-ray radiation to be emitted. The variation with the wavelength lambda of the intensity I of the emitted X-ray radiation is shown here. So this is a typical graph of X-ray radiation. There is a cut-off wavelength here. Explain why. Remember, the questions are always almost the same. The questions always be almost the same. Explain why there is a continuous distribution of wavelengths. So remember, we said when an X-ray is produced when electrons are decelerated or accelerated electrons collide with the metal target, there is a wide range of accelerations or decelerations. And remember, the energy of the wavelength, the energy of the X-rays depend on these decelerations. Therefore, the X-ray photons will have different energies, therefore different wavelengths. That's why we have a continuous distribution of wavelengths. So we can say an X-ray beam or an X-ray is produced when an electron is suddenly decelerated So if we have large accelerations, they will result in large photon energies. Larger accelerations or decelerations result in larger photon energies. Since there is a continuous range of decelerations, it results in a continuous spectrum of wavelengths. So since there is a wide range of decelerations, since there is a continuous range of decelerations, it results in a continuous spectrum of wavelengths. Okay, so because X-rays are produced when fast-moving electrons are rapidly decelerated, in other words, they have different decelerations when they collide with the metal target. And therefore, remember the energy of the X-ray photons depends on these decelerations. That means electrons which undergo larger decelerations will give rise to photons with larger energies, and electrons which will undergo smaller decelerations will give photons with smaller energies. For that reason, the emerging X-ray photons will have a wide range of energies as required. At certain wavelengths, there are narrow peaks of increased intensity. You can see the narrow peaks there. Okay, so we want to explain why there are narrow peaks. Remember, these narrow peaks were as a result of electron transition, but since these are 3 marks, we now have to explain in details. So these correspond to an electron in the inner shell of the target, which is excited on collision, and on de-excitation, the electron emits a photon. Since there only exists discrete energy levels of electrons, so the discrete photon wavelengths are going to be emitted. So these correspond to an electron in the inner shell. In the inner shell of the target, which is excited, on collision. An electron in an atom in an inner shell of the target is excited. In other words, it is moved to a higher energy level on collision. So on de-excitation, On the excitation, the electron emits a photon. The electron emits a photon. Remember, there only exist specific energy levels for these electrons. So since from quantum physics you saw that there exists discrete energy levels of electrons, discrete energy levels of electrons. So discrete photon wavelengths are emitted. There are 4 discrete photon wavelengths are emitted. So discrete photon wavelengths are emitted. In other words, during collision, an electron is promoted from one energy level to another energy level. Remember, the photon which is absorbed, or the energy which is absorbed, is equivalent to 2 different energy levels, because electrons only occupy specific energy levels in atoms. State one reason for using non-invasive techniques in medical diagnosis. Of course, non-invasive means they don't open up any body parts, they don't insert any instrument into the body. So it means there is a less chance of infection during diagnosis, and unnecessary scarring is also avoided. So there is less chance of infection, there is a less chance of infection during diagnosis. And unnecessary scarring is avoided. Unnecessary scars are avoided. Describe the use of medical tracers to diagnose the conditions of organs. Now, when we talk about medical tracers, that is now the PET scan. Note that in medical, a tracer is injected into the body where it is absorbed by organs. The tracer emits positrons which annihilate with electrons to produce a pair of gamma rays which are detected by the beta detector or the gamma camera. So here, using medical tracers, a tracer is injected into the body. Commonly, it is F18 or fluorine 18. So a tracer, remember, a tracer is a substance which attaches itself on organic molecules in the body, such as glucose or water. So a tracer is injected into the body, where it is absorbed. Where it is absorbed by organs, where it is absorbed by organs. So the tracer emits positrons because it has a short half-life, it emits positrons, that is beta plus, which annihilates with electrons in the body. So the positron annihilates, in other words, it combines with the electrons and their masses becomes a pair of gamma ray photons, which annihilates to produce pairs of gamma ray photons. And these ones are detected by the beta detector or detected by the gamma camera. So we call the beta detector or the gamma camera, whatever you want to call it. Okay. Describe the principles of PET. Describe the principles of positron emission tomography. Okay, so we shall describe this in details, but you can always, you may not easily describe everything in details, but I will describe this in details. However, you need to note that during a PET scan, the patient must be stationary in the tube, which is surrounded by gamma detectors or gamma cameras. And they will inject, of course, remember the patient is injected with a tracer as we have seen above. The tracer in the body has a short half-life, therefore it immediately disintegrates to give positrons. Note that these positrons travel a very short distance and they emit electrons, they annihilate. When they annihilate, they produce pairs or a pair of gamma ray photons. These gamma ray photons travel in a straight line, which in your class you call the line of response, and they hit opposite detectors. So an image of the tracer concentration in the tissue can be created by processing the arrival times of these gamma ray photons. Remember, when there are so many gamma ray photons coming from the same area, then on the image or the image produced on the screen of the computer will show a bright spot of that point where so many gamma ray photons have originated. Okay, so in details, we can now explain this. So the patient lays stationary in the tube surrounded by a ring of gamma ray detectors. The patient lays stationary in a tube surrounded by a ring of gamma ray detectors. It's a ring surrounded by gamma ray detectors. Once the tracer, that is normally F18 or fluorine 18, is introduced into the body, it has a short half-life. Once the tracer, in bracket that is F18, fluorine 18, is introduced into the body, into the body. It has a short half-life. It has a short half-life, so it decays emitting beta particles. So it decays emitting positrons immediately. That is beta positive. It decays emitting positrons immediately. The positrons now travel a small distance, so the positrons travel a small distance that's about a millimeter and annihilate. And annihilate when they interact with electrons. And annihilate when they interact with electrons in the tissues. When they interact with electrons in the tissues. Okay, so the positrons travel a small distance and annihilate when they interact with the electrons in the tissues. So each annihilation produces a pair. Each annihilation produces a pair of gamma ray photons. Each annihilation produces a pair of gamma ray photons which travel in a straight line. Which travel in a straight line. We call this the line of response. Which travel in a straight line in opposite directions. And hit the detectors. So an image of the tracer concentration in the tissue can be created. An image of the tracer concentration. An image of the tracer concentration in the tissue can be can be created by processing the arrival times of the gamma ray photons. So by processing the time which the gamma ray photons take to reach to the detectors, an image of the tracer concentration. When I talk about tracer concentration, is the area where the concentration is too much. Note that the arrival times indicate the location of the tumor. The arrival time the arrival times indicate or indicates the arrival times indicate the location the arrival times indicate the location of the tumor inside the body. That is the position of increased activity, to be precise. Position of increased activity. So the location of the tumor is that position where the activity has increased. Remember, we said the PET scan relies on the fact that the part which has a problem has a high body metabolism. And high body metabolism implies the rate of conversion of glucose into energy is so high. So that is a place of increased activity, and that is, if there's a tumor being diagnosed, then the location of the tumor is indicated by the arrival time of these gamma ray photons. Note that a three-dimensional image is going to be created. A three-dimensional image, a 3D image, is created by the computer connected to the detectors. A three-dimensional image is created by the computer which is connected to the detectors. And remember also that the more photons from a particular point, the more tracer that is present. The more photons from a particular point, the more tracer, in other words, the concentration of the tracer at that point is high. So the more tracer present, tracer present in the tissue, in the tissue which is being studied. And this will appear as a bright point on the image. It will appear as a bright point on the image. Okay, so that is the PET scan. So it is a long description, but it's easy if you master the basics. The basics are actually the same. Number next, describe the principles of ultrasound scanning. Now, ultrasound scanning, this is going to be, it is the same as using ultrasound for diagnosis. Using ultrasound for diagnosis, and we answered this question on page 517 on the first just when we had just started in part 1, page 516. So I will not repeat this. It is the same process. You look at the piezoelectric transducer, where an alternating field is applied across the quasi-crystal so that the crystal vibrates to produce ultrasound. A transducer, remember, is placed on the skin, which has been smeared with a gel to exclude air. Short pulses are sent into the body, where they are partially reflected and partially transmitted. And remember, the reflected pulses are the ones to be detected and converted into voltage pulses to process an image. And the time delay gives information about the depth of the boundary, yet the intensity reflected gives information about the nature of the boundary. So that one we have answered it. Using ultrasound in scan or to obtain diagnostic information, that is on page 517. Then FDG, that is fluorodeoxyglucose, is a radiopharmaceutical used for PET scans. It contains radioactive fluorine F18, which is a positron emitter with a half-life of 6.6 times 10 power 3 seconds. A patient is injected with FDG, which has an initial activity of 250 megabecquerels. Calculate the decay constant of fluorine. Now this is in nuclear physics. Remember, decay constant is equal to ln of 2 over T1/2 over half-life. If you remember from nuclear physics. So this is equal to ln of 2 divided by 6.63 times 10 power 3. And when we press our calculator, so this is giving us 1.05 times 10 power negative 4. 1.05 times 10 power negative 4. Show that the initial number of fluorine 18 nuclei in FDG is about 2 times 10 power 12. So we want to show that the initial number of fluorine is 2 times 10 power 12. So activity is equal to lambda times 9 times n, where n is the number of nuclei. So the number of nuclei is going to be equal to activity divided by decay constant. So the activity was given as 250 megabecquerels, so that is 250 times 10 power 6 divided by 1.05 times 10 power negative 4. So this is 2 point, check. So this is 2.38 times 10 power 12, which to one significant figure is 2 times 10 power 12 as required. Okay. About 9.9% of the mass of FDG is fluorine 18. About 9.9% of the mass of FDG is fluorine 18. Use your answer in B to determine the initial mass of FDG given to the patient. The molar mass of fluorine is 0.018 kilograms. So we can first of all find the mass of fluorine, but remember 9.9% of that mass, the mass of FDG is actually fluorine. What is the mass of fluorine? The mass of, I'll just call it F18. The mass of F18 will be now from nuclear physics, N over Na times the molar mass. You remember we said number of moles is mass over molar mass, which is the same as number of nuclei over Avogadro's number. Now I'm only taking this part here. So this is going to be 2.4 times 10 power 12. I'm just taking this part here, 2.4 times 10 power 12 times the molar mass, which is 0.018, divided by Avogadro's number is 6.02 times 10 power 23. That is the mass of F18. But remember, the mass of F18 is 9.9% of the mass of FDG. So we shall simply say that 9.9 divided by 100 of the mass of FDG should be equal to this value here, should be equal to 2.4 times 10 power 12 times 0.018 divided by 6.02 times 10 power 23. So in other words, I just divide by 0.99. So the mass of FDG is going to be 2.4 times 10 power 12 times 0.018 divided by, I'm dividing by 9.9 over 100, which is 0.099 times 6.02 times 10 power 23. So I press my calculator. So from my calculator, I am getting 7.2 times 10 power negative 13 kilograms. A typical PET scan takes 20 minutes. Determine the activity of FD in the patient after this time. A typical PET scan takes 20 minutes. So activity from nuclear physics and radioactivity, activity is equal to A naught e power negative lambda t, where lambda is the decay constant, remember. So this is going to be initial activity is 250 megabecquerels, so that is 250. It is mega, the answer is in mega, so I may not add times 10 power. So this will be e power negative, lambda was 1.05 times 10 power negative 4, that was lambda. Then times time is 20 minutes. So 20 minutes is 20 times 60 to change it to seconds because becquerels is per second. When I press my calculator, e power negative 1.05 exponent 4 times 20 times 60 times 250. Okay, so this is 220 megabecquerels. So this is 220 megabecquerels. Okay, positron emission tomography. Positron emission tomography can be used to locate the area of increased activity within the brain. Describe the principles of PET scan. In your answer, you should make clear how the position of increased activity is located. So we have answered a similar question on page 500, page 554. Just shortly, we have answered a similar question on page 554. So that one, I will not repeat it. It will be wasting a lot of time. So you just refer to the previous question, page 554. Okay. Next, technetium 99M is a common medical tracer injected into patients before they have a scan with a gamma camera. That is a PET scan still. Technetium 99 is a gamma emitter with half-life of about 6 hours. Each gamma ray photon has energy of 2.2 times 10 power negative 14 joules. A patient is given a dose with an initial activity of 500 megabecquerels. Explain what is meant by activity. Of course, activity, this is the rate of decay, the rate of disintegration of nuclei, or then it will now be the number of gamma ray photons emitted per unit time. The rate of decay or disintegration of a nuclei. The rate of decay or disintegration of nuclei, that is the number of nuclei decaying per unit time. Number of nuclei decaying per unit time. That is number of nuclei decaying per unit time, that is activity. It is, since we are now talking about gamma ray photons, because technetium is going to be emitting, is a gamma emitter. So we can also say this is the number of gamma photons the number of gamma photons emitted per unit time, because each nucleus will emit a gamma photon. So the number of gamma photons emitted per unit time corresponds actually with the activity or the number of nuclei decaying per unit time. So calculate the initial rate of energy emission from the dose of technetium 99, the initial energy. So they have given us each gamma ray photon has energy of 2.2 times 10 power negative 14 joules. And they have given us that there are actually, a patient is given a dose with an initial activity of 500 megabecquerels. So that means 500 times 10 power 6 nuclei are going to decay per second. That's what this one means. If this is the activity, then activity is the number of nuclei decaying per unit time. So 500 times 10 power 6 nuclei are going to decay in 1 second. So the energy, the initial rate of energy emission. So energy per unit time, that is the rate. That is energy per unit time is going to be the energy of each gamma ray photon, which is 2.2 times 10 power negative 14 times the number of gamma ray photons, which is 500 times 10 power 6 per second. That is over 1 second. So this is going to give us this gives me 1.1 times 10 power negative 15 as the rate of emission, that is in joules per second, the rate of emission of energy. Name and describe the functions of the main components of a gamma camera. Now, a gamma camera can be considered to be the detector of these gamma radiations which are coming from the body during a PET scan. It has majorly four important parts. It has the collimator, it has the scintillator, it has the photomultiplier, and of course the computer. Those three form what we call a gamma camera, or the complete detector of gamma ray photons during a PET scan. So let's begin with the collimator. What is its purpose? The collimator, to collimate is to put in line. So this one allows unidirectional gamma ray photons to travel along the axis of lead tubes. This allows unidirectional gamma ray photons to travel along the axis of lead tubes. So that's the purpose of the collimator. It is just going to allow the unidirectional gamma ray photons to travel along the axis of the tube. So those which are not in one direction, then they are not allowed. Number two is the scintillator, or sometimes it's called the crystal scintillator. The scintillator. So what is the purpose of the scintillator? So we know that a gamma ray photon incident on the crystal is going to produce just many photons of visible light, because a gamma ray photon is going to trigger an electron in the crystal, and the electron is going to pass through the crystal and trigger other electrons, exciting them. On de-excitation, these electrons will re-emit visible light or visible photons, or many visible photons. So a gamma ray photon incident on the crystal produces many photons of visible light. That is scintillation. Now, single gamma ray photon incident on a crystal will result into many photons of visible light. That is scintillation. Remember how I've said the process involves the gamma ray photon gives its energy to an electron in the crystal. As the electron moves through the crystal, it triggers or excites other electrons. When all these electrons de-excite, they re-emit visible photons, or photons of visible light. Then number three is the photomultiplier, or the photon multiplier tubes. The photon multiplier tubes, or photomultiplier. The photon multiplier tubes, like it's multiplying the photons. So the photons could be very faint and may need amplification. So photons produced, the photons produced by visible light the photons produced by visible light are very faint. So they need they need to be amplified. They need to be amplified and again converted into an electrical signal. And converted into an electrical signal. And this is the work of the photomultiplier tube. The photomultiplier tube. And lastly is the computer. So signals from the photomultiplier tubes are used by the computer to generate an image. They are used by the computer to generate an image. And of course, the quality of the image is going to be improved by using narrower long collimators, or using longer scanning time, because longer scanning time allows more activity to take place, more disintegrations, more annihilation processes, and so on and so forth. So we can say the quality, because the question told us in your answer, you should make clear how a good quality image can be achieved with these components. So we can simply conclude that the quality of images is improved by using narrower, longer collimators, or using longer scanning time. A typical PET scan takes about 20 minutes, but if we could increase the time of the scan, of course, more disintegrations would occur. We would allow more time for more activity to occur, so the quality of the image would be improved. Okay, that is that question. State two main properties of ultrasound. I think ultrasound is just like any other sound. It is longitudinal, just like any other sound. So it is a longitudinal wave. Longitudinal wave. Only that for it has a frequency greater than 20 kilohertz. So the other property is frequency greater frequency greater than 20 or 20,000 hertz. Those are the two major properties of ultrasound. So the figure shows an image of the brain using a positron emission tomography scanner. The lighter regions in the figure show the active areas of the brain. Fluorine 18 is a common tracer injected into a patient before a PET scan. Explain the basic principles of PET scanning. The basic principles of PET scanning, including how the image is formed. So we have explained this. We have explained this on page 554. I will not repeat it. Page 554. You can revisit it and see how the image is produced. Fluorine 18 is a common radioactive isotope used in positron emission tomography. Fluorine 18 emits positrons. A patient is injected with a radiopharmaceutical containing fluorine 18. Describe how a PET scanner is used to locate an area of increased activity within the patient. We have also answered this question. It is the same as PET scanning. That is on page 554. You can still revisit that. Okay. The half-life of fluorine 18 is 110 minutes. Calculate the time t in minutes for the activity of radiopharmaceutical to decrease to 30%. So we know from nuclear physics, activity is equal to A naught e power negative lambda times t. So the activity should be 30% of the initial if the initial is A naught. So this is going to be 0.30 of A naught equaling to A naught e power negative the decay constant. Remember, we know that lambda is equal to ln of 2 divided by t a half. That is over half-life. So this is going to be negative lambda, which is ln of 2 over time, which is 110, because we want the answer in minutes, over half-life, which is 110. And this is times t. So we introduce ln. So ln of 0.30, a naught has cancelled, is equal to negative ln of 2 over 110 times t. So you make t the subject. T is going to be 110 ln of 2 divided by negative no, not ln of 2. It is ln of what is wrong with this? So it is ln 110 ln of 0.30. I'm cross multiplying, divided by ln of 2 negative. From our calculator, so from my calculator, this is 190 minutes. PET scanners are not available in all hospitals. This is because fluorine 18 requires expensive on-site particle accelerators, and fluorine 18 has a small shelf life. In other words, it can't be stored for long. It has a very small shelf life. It requires expensive on-site particle accelerators to produce or to manufacture or to prepare. Suggest the impact this may have on treatment and diagnosis of patients in the country. Of course, it means that some patients may not get the treatment because of where they live, and this may also involve longer waiting lists. So that is ethical. That is an ethical issue. So some patients Some patients may not get the treatment because of where they live. And longer waiting lists. And longer waiting lists. So this may prevent some patients from undertaking the scan because of where they live and longer waiting lists involved. That is an ethical issue with the PET scan because it is hard it is very expensive to produce fluorine on site since it requires particle accelerators and it involves longer waiting lists. Therefore, some patients will miss out the treatment. Okay, the nuclear reaction below shows how the isotope of fluorine-18 is made from radioisotope from the isotope of oxygen. Oxygen-18 nucleus is stationary and the proton has kinetic energy 0.25 times 10 power negative 11 joules. So this is a very important energy for this reaction. The binding energy of the oxygen nucleus is this one. Remember, binding energy from nuclear physics, the energy released or absorbed when nuclei are separated to infinity or are brought from infinity. The binding energy of F18 is 220. On the other side, the proton and the neutron have zero binding energies. Explain why a high-speed proton is necessary to trigger the nuclear reaction shown above. Why a high speed? We know that high speed means high kinetic energy. Note that the proton and the nucleus have the same charge, so there is a repulsion. If the proton does not have high speed, then it will not come close to the nucleus for the reaction to occur. So we are saying the proton is repelled by the nucleus. The proton is repelled by the nucleus, but a high-speed proton a high-speed proton a high-speed proton has enough energy to come close to the oxygen nucleus. To come close to the oxygen nucleus for the reaction to occur. The proton is repelled by the nucleus, but a high-speed proton has enough energy to come close to the oxygen nucleus for the reaction to occur. In other words, it has enough energy to overcome the force of repulsion. It has enough energy to overcome the electrostatic repulsion from the oxygen nucleus so that the reaction can occur. Estimate the minimum wavelength of the gamma ray photon. So we need to look for the energy here. Remember, the most important energy is this one here. Then the binding energy on the left is 2.24 and on the right is 2.2. So the energy which is used in binding is the difference between this and this. Then we shall subtract that energy from the kinetic energy of the proton for the reaction so that the balance is given to the gamma ray photon. Therefore, the energy of the gamma ray photon is going to be equal to 0.25 minus the binding energies, which is going to be 2.24 minus 2.20. Of course, this will be times 10 power negative 11. So that is the difference, that is the energy which remains and is given to the X-ray photon. So the difference in this that is used for binding, the other side, or is given out as binding energy, or is required to form the fluorine nuclei. Then we subtract that energy from the kinetic energy of the proton to get the energy which is given to the gamma ray photon. And from my calculator, 0.25 minus 2 that is 2.24. So this is giving me 0.21 times 10 power negative 21. That is the energy. So we know that gamma ray, the wavelength is equal to hc over the energy, which is going to be 6.63 times 10 power negative 34, then times 3 times 10 power 8, divided by the energy, which is 0.21 times 10 power negative 21. And when I press my calculator, so this gives me 9.5 times 10 power negative 14 joules. Fluorine 18 is a positron emitter. Name a medical imaging technique that uses F18 and state one benefit of the technique. So this one is used in PET scans, used in PET. It is used in PET scans to detect. It is used in PET scans and basically to detect to detect cancer, to detect tumors, or to detect functioning, to study functioning, or to detect the functioning of organs, such as the brain. They said state one benefit of the technique. Of course, this is non-invasive. It is non-invasive and gives three-dimensional image. And gives 3D images. It is non-invasive in that no instrument is inserted into the patient's body during the scan, and it also gives three-dimensional images which can be viewed and rotated and viewed from any angle. Okay. The figure shows the circular track. The figure shows the circular track. The figure shows the circular track of a positron moving in a uniform magnetic field. The magnetic field is perpendicular to the plane of the figure. The speed of the positron is that one, and the radius of the track is 0.018 meters. State the direction of the force acting on the positron when at point A, and explain why this force does not change the speed of the of the positron. Of course, we know that the magnetic force is constant and always normal or perpendicular to the direction of motion. The force always acts towards the center. So the force is towards the center. The force is towards the center. The force is towards the center of the circle and is perpendicular or normal. Perpendicular to the motion or to the direction of motion. It's perpendicular to the direction of motion of the particle. In other words, no component of the force in the direction of motion. No component of the force is in the direction of motion. That's what it means. So there is no work done on the particle. Hence, no work done on the particle. So the magnetic force does not cause any work, does not do any work on the particle, so the kinetic energy of the particle does not change. And if the kinetic energy of the particle does not change, it means the speed does not change. The magnetic force just provides the centripetal force. So calculate the magnitude of the magnetic flux density of the magnetic field. So we have said that the magnetic force provides the centripetal force. The magnetic force provides the centripetal force. So we shall say that BQV is equal to mv squared over r. So B, which we want to find, is going to be a 1v as cancelled. That will be mv divided by r times q, which will be the mass is 9.11 times 10 power negative 31. The speed was given as 5.0 times 10 power 7. The radius was given as 0.018 meters, and the charge of the electron of the positron is 1.6 times 10 power negative 19. So press our calculator. So this is giving me a 1.6 times 10 power negative 2. 1.6 times 10 power negative 2. At point B, the positron interacts with the stationary electron and they annihilate each other. The annihilation process produces two identical gamma ray photons traveling in opposite directions. We call that the line of response. Calculate the wavelength of the gamma ray photons, assuming the kinetic energy of the positron is negligible. So the energy of the two photons the energy of two photons is going to be equal to that is twice hf, which is twice hc divided by lambda. That's the energy of the two photons. But remember, it is coming from the positron and electron interaction. And the energy of the positron electron interaction is going to be m, mass of the particles, times the speed. But because they are two, that will be twice m. So 2mc squared is going to be equal to hc over wavelength. So 2 has cancelled, c has cancelled, 1 c has cancelled. So we have that the wavelength lambda is going to be equal to h divided by m times c. We now substitute. So this will be 6.63 times 10 power negative 34, that is Planck's constant, divided by 9.11 times 10 power negative 31, that is the mass of the particles or the positron electron interaction, then times 3 times 10 power 8, that is the speed of light. So I press the calculator here, and this is giving me 2.4 times 10 power negative 12. 2.4 times 10 power negative 12. Okay. Lead of different thicknesses can be used to investigate the absorption of gamma photons from a radioactive source. The figure shows a graph of gamma photon energy against the half thickness of lead. Half thickness of lead is the thickness of lead which will reduce the original count rate by half. We have photon energy in mega electron volts and half thickness of lead. Describe an experiment that can be carried out to determine the half thickness of lead and how you would use your results to determine the energy of the gamma photon from a radioactive gamma source in your laboratory. Include the equipment used, any safety precautions necessary, and the quality of how the quality of the results may be improved. So this is more of a planning question, but we shall still get a clue about it. We shall get a clue about it. So we may need some of the following apparatus. We may need a GM tube, that is a Geiger mirror tube, GM tube. We may need a GM tube. We may need a GM tube. I don't know what is wrong with my pen. We will need a GM tube. We will need a retimeter because we are going to be looking at activity. Of course, we shall need the lead plates. We may need a micrometer or vernier caliper. Micrometer screw gauge or a vernier caliper. I'll write VC for vernier caliper. This one will be to measure thickness, basically. To measure thickness. So let's talk about the procedure now. The procedure, we shall measure. In our procedure, we shall measure the counts for a specific time and hence the count rate for each thickness of lead. Measure. Counts. We shall measure counts for a specific time and hence the count rate for each thickness. Of lead. Of course, we shall vary the thickness of lead and record the count rates. Vary the thickness of lead and every time record the count rate. So that is the simple procedure we shall need. And how we shall obtain results, we shall now plot a graph. Plot a graph of count rate against thickness. Count rate against thickness, and from the graph we shall determine the half thickness of lead. And determine the half thickness of lead. Then we shall now use the figure above to determine the photon energy. Use the figure above, we shall use the graph above to determine the photon energy we shall use the figure above to determine the photon energy. From the graph, remember we have determined the half thickness of lead, and from the figure above we have determined the photon energy. Now if we want quality results, So for quality results, for quality results, record the counts over a long period of time. Record counts over a long period of time. Record counts over a long period of time, and also remember to remove the background radiation. And also remove background radiation for each count. Okay, you would remove background radiation for each count. Then how about for safety? Because you may also want safety precautions. For safety, because remember you are dealing with the radioactive substances, so we shall say for safety, do not point source at any person. Do not point the source of radiations at any person. You need to keep a safe distance. You can also keep a safe distance between you and and the source. You can also use tongs to handle the source. Because you are dealing with radioactive substances, you can't interact with them directly. So you keep a safe distance between you and the source. Use tongs to handle the source. Do not point the source at any person. Those are some of the safety precautions. Last page. Fluorodeoxyglucose is a radioactive tracer often used for PET scans. It contains radioactive fluorine-18, which is positron emitter. Some information about FDG and fluorine-18 is given here. So they have given us that 9.9% of the mass of FDG is fluorine. The half-life is 600, and the molar mass of fluorine is given as that. A patient is injected with FDG. The initial activity is 400 megabecquerels. That is 400 times 10 power 6 becquerels. Use the information given to calculate the initial mass of FDG given to the patient. So first of all, we need the mass of fluorine. We need the mass of fluorine before we now find the mass of FDG. So the mass of fluorine. First of all, the mass of fluorine, which is I'm going to call MF18, is going to be the number of particles, nuclei of fluorine over Avogadro's number times the molar mass. We don't have N, number of nuclei of fluorine, but N can be got from activity is equal to lambda times N. And we don't have the decay constant, but we have half-life. Then we know that the decay constant lambda is equal to ln of 2 divided by half-life, T a half. So this is going to be ln of 2 divided by half-life, which is 6600. That is a decay constant. So it means we now know that N remember is activity, which is given as 400 times 10 power 6. 400 times 10 power 6 will be divided by the decay constant. So I'm dividing by decay constant. So in the denominator, I will have ln of 2, and 600 goes 6,600 goes up. That is N. So therefore, it means that the mass of F18 is simply going to be equal to N, which is 400 times 10 power 6 times 600, 6,600. Okay, let me write this one to look better. So this is times 6,600 divided by ln of 2, that is N alone. So times the molar mass, so this will be times the molar mass, which is given as 0.018 time divided by Avogadro's constant, so this will be over 6.02 times 10 power 23. That is the mass of F18. Okay, now it means this mass should be equal to 9.9% of FDG. So it means 9.9% of the mass of FDG is fluorine, and 9.9% is 0.099 of the mass of FDG is the same as the mass of fluorine. So this is going to be equal to this value here. It is going to be equal to this value. Let me just press the calculator to get this value here. So 400 exponent 6 times 6600 times 0.018 divided by ln of 2 divided by 6.02 exponent 23. So this mass here is 1.1 4 times 10 power negative 13 kilograms. So the mass of 0.099 mass of FDG is mass of fluorine. So this is 1.14 times 10 power negative 13. So I divide this by 0.099. And this gives me a 1.15 times 10 power negative 12. In other words, precisely it is 1.2 times 10 power negative 12 kilograms. So that is the mass of FDG. That is the mass of FDG. I've just divided both sides by 0.099. Last but not least, PET scanners are expensive because they require nearby or on-site particle accelerator that produces fluorine-18. Discuss the ethical issues that this raises in the treatment of patients. So we have already said that not all patients will be able to undergo this scan because of their location. This would involve long waiting lists and so on and so forth. Because fluorine-18 has a small shelf life. It can be stored in the shelf for a small period of time, so not all patients will have access. Not all patients will have access to the scans due to location. Not all patients will have access to the scans due to location. So that marks the end of medical physics. For further questions in medical physics, there will be just short tests which I will record also for you to also refer to them because the unit is, especially PET scan, is still new. So any new questions that appear will be discussed later on in the next videos. However, our next video will be actually astrophysics and cosmology, and it will be just one video. Don't forget to subscribe, share the video, download the document, print it in hard copy for practice. Thank you. Have a good time.